So today we have an old colleague and friend of mine, Tony Lavoie, actually got his engineering degree in the Aeroastro department here in MIT. So this is coming back home for him, and he actually grew up in Massachusetts. But for the last 23 years, he's been in Huntsville, Alabama, at the Marshall Space Flight Center, and actually has been an engineer on quite a few of the projects that I've flown with, including the Astro Observatory and the tethered satellite. And Tony has continued to rise up in the ranks of the NASA engineering community. He is now the, I guess, program manager, right? Project manager for the robotic lunar exploration program. So if you've been following the space news, Marshall Space Flight Center is going to be developing the first robotic lunar lander that we have ever sent to the moon since Surveyor. So it will be, what, like 40 years, I guess, we haven't done that, and we're going to have to figure out how to do it. So Tony was also the chief engineer on the Chandra X-ray Observatory, which was launched on the Shuttle. And so I thought it would be interesting to hear, since we've been looking at many other aspects of space shuttle operations, to hear something about what it was like getting a payload ready to fly on the shuttle. But also we were discussing before class began that he may have some comments on the robotic lunar exploration program, which is now in the pre-phase A studies, and it will be interesting. You know, we talked a lot about what it was like in the pre-phase A in the early days of coming up with the requirements for the shuttle, and clearly in systems engineering, getting your requirements right is one of the key goals for success. So Tony may have some comments on that. So I've talked enough. Tony, you got it.
Okay. Hi there. We're going to start talking about Chandra, and as Jeff pointed out, I'm going to also talk about my new challenge, my new assignment as project manager, and in pre-phase A, what that means. So, and I think it's a lot different being a student where you have a single closed form solution and you go and you work a problem and it's done. In the real world is you seldom, if ever, work a problem one time and have it finish. And we'll get into that as we go along. Okay, I'm going to talk about Chandra X-ray Observatory, and these are just a few images that Chandra has produced. It's an outstanding X-ray imager, and it has been flying since July of '99. And you're going to get all the gory details and all the lessons learned that we had in working that project. Okay, so I'll do an overview, Chandra history, and then the challenges we faced and the lessons learned associated with that, and we'll cover those topics. And in terms of how we operate, feel free to ask questions as we go along. It's kind of loose and easy. Chandra, or back then it was AXAF, Advanced X-ray Astrophysics Facility. NASA, by the way, loves acronyms. So, I mean, if you're interested in working with NASA or associated with NASA, they just acronym crazy. So, AXAF was one of the 4 great observatories. The 4 great observatories were meant to cover as close to the entire spectrum as NASA could. And so the visible great observatory is Hubble. And ultraviolet, that's true, little ultraviolet. The X-ray observatory is AXAF, which was later named Chandra. The gamma ray observatory is Gamma Ray Observatory, and I can't remember what the name of it was. Compton Gamma Ray Observatory. Yeah. And the last one was infrared, and that originally started off as Certif, and now it's Spitzer. and that was launched a few years ago. So in each of the 4 great observatories, there is, or there was, they were higher class than most of the other science missions, even the science telescopes, and NASA did invest quite a bit of money on each of those, and so you'll see that the performance from the 4 great observatories are, in terms of quality, probably the best in the world and the best NASA's ever done. So for the X-ray region, Chandra, or AXAF, was built. And its objective, you start with program objectives and you work down with science objectives. The science objectives were really to understand the nature of the universe and determine the nature of celestial objects, in particular those that are hot, and hot objects will produce X-rays. And of course Jeff knows all about that. If you have any questions related to that, you can ask Jeff. But from an engineer perspective, what happens is you're given a set of objectives and maybe a program objective, and now you have to craft a mission and craft a project from those. And one of the problems that you face is that sometimes they're not crisp, and sometimes they're flexible based on cost, and also sometimes they're not very specific, like determine the nature of celestial objects from stars to quasars. Well, okay, now what? But this is the kind of thing that typically you start with, and you have to iterate with, in this case, the science community. If you're building part of the shuttle, you have to iterate with, for instance, the users, the astronauts, the payload developers that would use the shuttle, the operators, etc. But the process is the same. You start with the top level objectives and you work your way down. Now again, because of the nature of what we're talking about, it's usually a very iterative process, and that can last for several months and even several years if there's a technical challenge that causes you to stretch out.
And AXAF certainly stretched out.
And I'll talk. We'll mention when it started. In terms of AXAF, kind of the key parameters are the percent encircled energy, i.e. how sharp is the image. Registration, meaning where's the target in the sky, and you got to remember that X-ray astronomy is a relatively new branch of astronomy because of the atmosphere. It absorbs X-rays. So we NASA, or we humans, only discovered X-ray astronomy in the last 40 years. So we need to go outside the atmosphere to get information on X-ray astronomy. So one of the things that we didn't know is, okay, if there are some X-ray sources there, they may or may not be the same sources that also emit invisible light. And if they're not, then you have a question of, okay, you kind of know there's a source out there, but you don't know where in the sky it is. And so one of the challenges that AXAF had was, okay, even if I have no stars around this X-ray source, I've got to be able to pinpoint where that X-ray source is. So that was a particular challenge that we had, trying to figure out how to do that. And that's what registration means. And then effective area is related to how many photons you can collect to make a good image. And recognize that if you're looking at the sun is very close, so you can get a lot of photons. But if you're looking at something that's 10 billion light years away, you're not collecting very many photons. So you have to wait a long time to get those photons, unless you have a big collecting area. So those are kind of the key performance requirements that you have to address when you're building an X-ray telescope. From those, there are key derived requirements that have to be derived basically to be able to maximize the scientific performance requirements. And so from these pieces of information, you derive mirror size and design, you derive focal length, pointing and control requirements. How accurately do you need to point thermal stability, because that plays a role in orbit, a very big role. Instrument sensitivity, and the fiducial transfer system, which I'll talk about later, which is the thing that allows you to do the registration, even the absence of local visible stars around it. Once you have the bulk of the science performance requirements and the derived requirements from these performance requirements, then you fill in kind of the rest of the pie, if you will. And those can be safety requirements in the case of a manned program. In fact, that's pretty significant, and it is a pretty significant cost driver for things that fly in space. Unfortunately, they also cost a lot to make sure they're not a hazard to the crew that flies. There are also construction standards, design and construction standards, which also turns out to be a big deal. So, for instance, if you're building a satellite and you have circuit cards, you're going to have requirements on soldering. You're going to have requirements on integrated circuits. You're going to have requirements on glazing. You're going to have requirements on bonding. You're going to have requirements on how to do things across the whole gamut of the spacecraft, not just the spacecraft, but also the shuttle and anything that flies up there. So for a given mission, there are probably on the order of 100, 150 separate documents that describe various things, design and construction standards, that you have to go through for a particular piece of building the vehicle. And so those things are always a challenge for a project manager, because the engineers want to get the latest standard that applies, and in excruciating detail, as engineers love to do. And yet from the project manager standpoint, we're trying to maintain cost. So there's always a trade-off between, well, okay, how good is good enough? From a program manager's perspective, better is the enemy of good. Yet from an engineer, good is always better, or better is always better. So there's always a healthy tension between the project manager and the engineers. And I would say that a successful project knows how to trade off. The project manager and the engineers know how to balance that tension to be able to get the best product. And we've done that before, and we've also imbalanced it and had some spectacular failures. Okay, once requirements are set, then you can start kind of designing and starting putting the drawings on and developing the system, if you will. But no, that's the kind of the general flow of information for a science payload or a science mission. Is you start with the top level requirements for performance, the scientific performance that you're looking for. From those you derive the direct performance requirements like what you see here, and then everything else cascades below that. And once you have the requirements set, then you can start developing concepts. Now, this was a preliminary design of ACSAF. I'm not going to talk about it, but I'm just going to show the next slide as to what it looks like now. And so you can see that there is a major difference between what it started out as and what it ended up as. And this is typical. It is not atypical. And the reason is cost. A lot of times when you're first starting out with requirements, you kind of don't know what the cost of the mission is going to be. And so you come up with an idea that has a lot of capability. This was orbit serviceable. It was in low Earth orbit, and it had 4 focal plane instruments that you could select, and it would actually move, much like Hubble. And it was a 15-year mission with reservicing with the shuttle astronauts. But when you start putting that on paper and you start crafting the requirements, one of the things you do in the early phase of a program is you also cost, or you try and cost, what those requirements result in terms of design. So even though you don't do the final design or you don't start working on the design in detail until after you've got the requirements set, in practical terms, you have to still put together a concept design so that you can cost it. And that's exactly what happened on AXAF. We put together, in parallel with working the requirements, we put together a design, and we costed the design. And it turned out that that was more money than NASA could afford. And so, as is typical, the iteration process begins with headquarters to change the parameters of the mission, to, in a sense, compromise the scientific objectives a little bit in terms of implementing a requirement set. And the result is, finally, you get something that you can pay for and that still meets the intent of the objectives, the scientific objectives. So, I mean, that's a key lesson to learn, is that when you're first starting out and you're first crafting what you want to do, expect it to change. And the key there is it's usually cost-driven as to what you can afford. So, not only that, NASA, just by the nature of what it's doing, since it's never built an AXAF before, it's really hard to get a good accurate cost of what it costs. So a lot of times the cost is derived from a parametric, usually weight-based system, such that, for instance, if the mirrors or if the solar arrays, you want them this big to provide this much power, okay, that big means they have to weigh, they mass so many kilograms, and so that's about, you know, X amount of dollars based on weight. Now there's a lot of additional factors that you put in, like complexity, interfaces, etc., technology readiness, whether you're looking for state-of-the-art or something that's has already flown. But generally, it's what's called a parametric cost model. And it's not based on taking a look at all the design drawings and saying, okay, this costs this much from the vendor, this costs this much, and you put it all together. That's called a bottoms-up assessment, and it's more accurate, but it also relies on having an accurate design picture, which obviously you don't have early on in a program. So, I mean, it's almost like a black art to try and take a requirement set and go through the requirements set and craft a design early on, or at least bound the design and bound the cost. Because again, early on what you're trying to do is get into the cost envelope and still meet the scientific objectives of the objectives that you're trying to do. Yes?
In this final design, how's this, other than the shape, how are its capabilities less than the original? I mean, because you didn't put as much money into it. So.
Correct. To make it on-orbit replaceable means that all of the boxes that you see in the spacecraft bus, or a lot of them, would have had to have been on this picture. They were all replaceable. So you have to spend some money making sure that the drawers slide in, slide out, there are no sharp edges, and it's accessible, etc. So packaging is important. So that is one area where you can reduce cost and not really have an effect on performance per se. However, one of the big areas that we did take a little bit of hit on performance is in the mirrors. Now, X-rays, you can't just have a regular shaped lens. You have to have what we use is grazing incidence mirrors because, and I'll explain this later, because the X-rays are so highly energetic, you have to graze them gradually to a focus. And we had, original concept had 6 mirrors nested. There were basically parabola shaped. The final concept had 4. We had to remove 2 of the, not the inside or the outside, but 2 of the middle mirrors. So the mirror set is 4. This orbit that this thing flies in is a highly elliptical orbit. It's about 140,000 kilometers by 10,000 kilometers. The original orbit was in low Earth orbit, which is about 350 kilometers. And so that affects the viewing time. But I think in all of the other registration, in encircled energy, I think that we still were able to meet the original objectives of the scientific mission. So there are ways to compromise that don't really affect directly what the scientists want to do, but it is a trade-off. It's usually not their first desire, but they signed up to it, they're comfortable with the final answer. Okay, explaining a little bit of how it's put together. This is a rather simplified version. Here are the solar arrays, that's where we get our power. This is the spacecraft bus. This is the HERMA, which is the mirrors, the nested cylinders that I was talking about earlier. This is a grating, low energy grating and a high energy grating. For spectroscopy, what you want to do is you want to bin all of the photons in a particular energy, much like a prism does for visible light. And the way you do that is with these facets there's probably 1,000 facets on this, and I've got a picture of that later, and you flip it into the beam when you want to get some spectroscopy data, and you remove the grating when you want to get an image, an X-ray image of what you're looking at. So, and that's a function of what the scientists want to do at a particular target. Some scientists want to get an image because that conveys more information for them than spectroscopy. Others want to see a spectrogram of the image because that tells them what the photons are and what the energy of the photons are, and that can tell you, for instance, what elements are present and what temperatures for a given, gas cloud or neutron star or what have you. And then we have an optical bench, and all that means is a piece of structure that's very stiff, because obviously you can tell if you flex a lot, that sure doesn't help your camera imaging the performance. So it's got to be very stiff, and that's why they call it an optical bench. And the ISIM is the Integrated Science Module, so that's where the instruments sit in Chandra. And here's a picture, as I mentioned before, of how the X-rays graze off of the cylinders in the HERMA down to a focal point about 10 meters away. Okay, Jeff had mentioned that sometimes it takes quite a while for science to come to fruition in a mission. And this is probably a good case. It started in 1978 with some concepts. We did get approval for New Start in 1988, so you can tell there was 10 years' time where this was just an idea in a scientist's mind. And typically the course of events is that the scientist lobbies and submits papers, submits proposals to NASA, lobbies Congress, lobbies National Science Foundation to say, hey, this is a good idea, we should do this. And here's the concept. And of course that concept changes over time as you get new technology, etc. And so that's exactly what happened here. We did get approval 10 years from when the original concept started. Authority to proceed for the prime contract was in January 1989. What this means is that that's when we hired a contractor to build the spacecraft. And the start of that process is called ATP. We had two separate ATPs. Sometimes you can say, okay, I can let out one contract to a company and let that company buy the science instruments, or I can compete the science instruments separately. And in this case, there's various pros and cons, but in this case, NASA decided to compete the instruments separately. From an engineer's point of view, one of the things that should pique your interest or note that when you have separate contracts, you always have a question of integration. Okay, if you're going to compete separately, you're going to have two separate pieces. Who's going to integrate them? The integration job will be harder when you compete them separately. Now, your performance is probably better when you have direct insight into the instruments and direct insight into the spacecraft contractor. But the penalty is, okay, now when you integrate the two, you have to make sure that works. And so as a project manager, as a systems engineer, you have to make sure you apply enough resources to make sure they work together and continue to work together as they're defining the interfaces, for instance, between the two elements. This was interesting in that in order to get it funded, NASA said, or Congress said, okay, we'll let you build an ACSAF, but along the way, you have to do some testing to show that you can meet the performance that you say you can meet. And so we were required by law to have a test of the mirrors in June of '91. And we also had another test later on, same thing, to verify that we could get the performance that we showed on paper with actual hardware before we committed to fly and before NASA committed to spend the rest of the money to fly. And so sometimes that happens. Sometimes if you have a smaller program, it doesn't go to Congress, so you don't get into those things. But when you have a great observatory and NASA spending a lot of money, a lot of times Congress will get in and say, yes, but. Yes, you're constrained, but. You have to show me along the way that you can do this. I wouldn't be surprised if Congress does that for the CEV, the new vehicle coming up, or the CLV. In fact, for the CLV, the launch vehicle, there's a push to have a demonstration test early just to verify that we can do it. Okay, now during this time, of course, we're still formulating requirements, and we rack up the cost, and lo and behold, NASA can't afford it. So we went through a program restructure at that time, where we dropped a couple of the mirrors, we changed its orbit, we removed crew servicing, and you could tell that the whole shape of the spacecraft changed. And again, that's unfortunately not atypical. It happens quite often. Okay, now, as you've probably heard with previous, yes?
What was the reason for the orbit change?
Good question. In orbit, there are Van Allen radiation belts, and we really can't observe too well within those belts. Now, in the first mission, the low Earth orbit mission, we're below the belts so we could operate. But the problem with low Earth orbit is you have this big Earth, you're close to Earth, and so you need power from the sun, and guess what? The sun goes behind the Earth. And so you're eclipsed for a good percentage of the orbit time. So when we had a mission, a 15-year mission in low Earth orbit, we said, well, since we don't have servicing, the lifetime cuts down to 5 years. Now, if I'm 5 years in low Earth orbit, I've just lost 2/3 of my mission time. So let's see if we can crank up the orbit, get as far outside the radiation belts as we can, and then we have basically 100% visibility the whole orbit if we can get completely outside. Problem with that is that costs propellant, because the radiation belts end around, they breathe, but roughly around 60,000 kilometers. So we could raise apogee to 140,000, but we didn't have enough money, gets down to money again, to raise perigee. So perigee stayed at about 10,000 kilometers. The resulting orbit time, if you looked at the integral of time outside the radiation belts, was probably about 70%. So it was a compromise. We did end up losing some overall time, but we did get performance outside about 70% of the orbit is usable for viewing. So that's the strategy, and that's why we went to a different orbit. So as you can tell, there's a lot of things that are traded off during that time to fit within the constraints that you've got. And again, that's typical. Okay, the 3 reviews that are kind of standard reviews for all programs and projects are, you start with a requirements review. And that's pretty basic. It's held early on. Requirements have started before that review. For science missions, you start with science objectives and you're percolating science requirements. And the system requirements review is really a review that baselines, if you will, and sets the requirements as firm as you can. And it's usually after you've gone through the cost gyrations. But it is done prior to doing any of the design reviews. So once you have a requirements review done, it was in December of '92. Almost 2 years later, we had what's called a preliminary design review in November of '94. The third review is called a critical design review in February of '96. What makes a preliminary design review and critical design review has to do with the maturity level of the design. For critical design review, supposedly you have on the order of 90% of your drawings complete and on the order of 10% of your hardware built. And I think for PDR, it's about 10% of your drawings built, the final drawings. So that kind of gauges what you're talking about there. And it's a typical milestone that NASA uses for all of its programs. Usually, these are set early on in the mission, in the program milestones, and for political and for programmatic reasons, you tend not to deviate. You try and meet those milestones, even if the project is not as mature as you'd like. Usually that's one that you try and keep hold of. So maybe you don't have 10%, maybe you have 5%, or maybe you don't have 90%, you have 70%. So sometimes you do go and you hold the milestone, you hold the review, but when you're not mature enough, sometimes you have to hold a delta review to catch up. And that's, again, something that NASA does for various reasons. If the situation is right, sometimes you can slip and allow a single review at the right time. Most often it's driven by non-technical things that require you either by your customer at headquarters, doesn't want you to slip, so you tend to hold it where he said he wanted it. And then we had the mirror delivery to the calibration facility in November, and it shipped the whole thing to the Cape for launch in February, and we launched in July. So you can see we spent about 5 or 6 months down at the Cape integrating into the shuttle, testing, and then we flew in July of '99. Those are the orbit parameters. We achieved the final orbit August 7th, so you can see about 2 weeks. And the way we did that is the shuttle only puts stuff to low Earth orbit, so you need some additional propulsion. We had an upper stage that got us part of the way there, used most of the energy. However, it wasn't at the final orbit. So integral to the spacecraft, we had a propulsion system that had to do 5 additional burns to get us to the final altitude and the final orbit parameters. So that's why it took us about 2 weeks, and again, that's not atypical, is when you're not operating in low Earth orbit, it takes you a while to get your final orbit. And these are a couple of interesting parameters. Safemode, talk a little bit about that. Spacecraft are designed such that if,
No, I'm just wondering if the inclination affects the requirements at all. Or does it not really matter? So it just stays at the same as the shuttle orbit.
The 28.5 is driven largely by the launch site at Kennedy Space Center.
Right. I'm just wondering if the science requirements could drive the inclination a bit.
Yes, for some missions, yes. We were fairly insensitive to that as long as we took advantage of launching at KSC at the optimum inclination. But there are missions like Space Station, because you have a launch from KSC and a launch from Russia, to optimize the performance of both launch centers, then the orbit is 58.5. Now, what that means to KSC launches is you pay a significant penalty. You pay about a 30% weight penalty for launching at KSC to the space station. So sometimes the answer is yes, you can optimize inclination, and sometimes when you have a large program and multiple launch sites, it's a compromise. So it's not efficient for each site. I was mentioning spacecraft typically have their avionics systems, and typically they do not contact the ground. They're not in communication with the ground all the time. And so for Chandra, that's the case. We may have, quote, contact with Chandra probably about 5 to 10% of the time per day. So in the meantime, figure that 90% of the time it's out of communication range. Now this is something, by the way, that's somewhat different from a manned mission. The manned missions tend to optimize and maximize communication coverage. So when Jeff's flying in the shuttle, we probably have 90–95% coverage over an orbit and over a day for communication. But in science missions, typically, rarely is that the case. And so what that means is the whole philosophy of operating a science mission is based on stored commands. And so we send up a stored command load, and that load's good for a day. And basically it steps through and automatically executes based on time. What that also means is you have to design a spacecraft to recognize when it has a problem. If a hardware box has a failure, it's got to be able to recognize that and go what's into a safe mode so that the ground can then recover and configure the systems to continue to operate. So that's one part of flying a spacecraft, is building a robust safe mode to be able to do that. And our first problem occurred in August 17th, 1999. Now note, it was ground error, as usually the case. Spacecraft are pretty complicated, and we probably had 400 or 500 separate procedures and commands on the ground for doing certain things. And even though we try and test them out individually, the combination of those procedures and in the execution, sometimes you put the spacecraft in the wrong configuration with one sequence, and then you follow with another sequence, and lo and behold, the software that you've designed for safe mode says, I'm in the wrong configuration, sorry, I'm going to safe mode. And so that happens. We've had only probably 3 safe mode events for 6 years, so that's not too bad at all. Hubble, for instance, has had probably an order of magnitude more than that. I think we've gotten smarter based on our design of Hubble to design this. But again, typically spacecraft do have safe mode designs in them. Given our orbit, we still have a small eclipse season. Twice a year, in the fall and in the spring, we have eclipses. And so our first eclipse season was then. Okay, this is the translation mechanism for the science instruments. This is where the telescope is. I won't go through that. This is kind of where we purchased, or we contracted for the various instruments. This is a CCD imaging spectrometer. In fact, this was it was both Penn State and MIT that produced this one, and that's one of the focal plane arrays or focal plane instruments, and the other one was a high-resolution camera using micro-channel plate technology instead of a CCD, and that one was from SAO just down the street in Cambridge. The high-energy transmission grating, as I had mentioned, was also from MIT. And the low-energy grating was from the Netherlands. And this is a good point to make also, is that a lot of times for science instruments or for science missions, NASA tries to lower the cost of the mission. And the way you can do that is you can reduce requirements, or you can get a partner and have the partner pay for an instrument that you want to fly. And so in this case, as is typically the case for science missions, NASA tries to go and get partners, international partners, that will bring to the table an element or a piece of hardware or some software that reduces the overall cost of the mission, but at the same time maintains its capability. So that's what we did with the low energy transmission grading. We got the Netherlands to basically design and build that and fly that. In exchange for that kind of arrangement, they get a percentage of viewing time that they can say, okay, for 5% of the viewing time, we get to point the telescope to wherever we want. And so typically that's kind of the handoff between our international partners and NASA in trying to reduce the overall cost to NASA for a given mission. And these are the gratings, as I had mentioned, and there's a bunch of facets along these. Now notice these are the 4 mirror shells, or they co-align with the 4 mirror shells, the innermost and the outermost. And this is kind of how it works. The gratings get flipped in, and this is the array of CCDs. Each one of these is a CCD, and the pattern of light, or the pattern of X-rays, follows along these lines when the X-rays actually come in. So that's what actually you see. Now, Chandra does have a ground system architecture. We communicate with the Deep Space Network. That's how we communicate, because it's not in low Earth orbit. So we can't use the satellites that are around the Earth. We get that signal from that satellite, and it's beamed to the control center here in Cambridge, in fact, and we do various things on the data. We process it out and send it to the general observers. Now, the way this operates is that every year, this control center, or the science folks operating the control center, solicit objectives. Okay, science community, come and request time and give me a proposal for viewing time for what you want to do, what target you want to look at, what are the configuration of the instrument, which instrument, etc. And so the Chandra folks go through and they probably collect about 800 proposals a year from all around the world. They will select roughly about 200, and it's not based on numbers, it's based on time. You have a certain amount of seconds in a year that's available, and so some of these proposals have large times, some have small times, but roughly it's about a 4-to-1. About 200 are selected, 800 are proposed, so that's good. You're oversubscribed. You have a lot of interest. NASA does fund those that are selected. So if you're a PI and you say, I want to go look at Crab Nebula, or I want to go look at a quasar somewhere, and you've got, and here are the reasons, here's what that will tell me. And it gets selected, NASA will fund you some money to be able to do that observation and process the data and publish. Now, NASA won't fund any that were selected from foreign countries. So the foreign countries, they have to get their funding, but we will allow them viewing time. And that is also typically the case. And by the way, all of these scientists across the world never have to come to Cambridge. It's all done electronically. They don't get their data real time. They get it probably a few weeks after the observation. And the reason for that is there's a lot of processing. You don't actually send, or you can, but usually you don't send the raw data out to the user. It's heavily processed, and the products of that processing are what is actually sent out. Now, there are tools that the control center also provides, but generally it's the processed data that's sent. Yes?
What sort of data is this? Images or numerical data, or?
It's data that can be used for images. It can be used for registering each photon, what energy it is. There is a lot of different choices of data, and some of the data is overlapping, but it does give you information on energy, location, number, count, where in the field. It can be used to then process an image or process a spectrogram, and you do that by using the tools that are also provided. It's like a viewer, or it's like a piece of software that allows you to view what's in that data. But the data is just the raw data. It's just a series of tables. Okay, and as we said, it began in 1978. I picked a prime and was given a new start. I'm not going to go through these. It was restructured. We went to 4 mirror pairs. We dropped 2 focal plane instruments, dropped the servicing requirements. I mentioned that. Interestingly enough, one of the instruments, we wanted to create a separate spacecraft just for that instrument. And believe it or not, the addition of this spacecraft and this one for the spectroscopy mission was going to be cheaper than the original concept. But again, due to cost, we continued this spectroscopy spacecraft for about a year to 2 years, and then that was cut due to cost. So we ended up flying just this one spacecraft, and the result is the Chandra Observatory that we've got now. Note that sometimes it's not within your control as to whether your program is canceled or not. We were doing quite well. It was within our cost envelope that they had given us, but at the time there were other priorities at NASA, and there were other overruns at NASA, and they have to weigh. Sometimes they say, well, you can have this much money for these many years, and every year they reevaluate, and that's because you don't know how much things are going to cost, because NASA typically builds one kind of a things, and you don't know really how much it costs until it's already done. So that reevaluation process continues now, and will probably continue for as long as NASA flies. So imaging and spectroscopy is what we do. Why is imaging so important? Well, clearly this image was a ROSAT image with the highest technology at the time, and here is the Chandra image, and you can see the neutron star right there, and there's no way that you can see a neutron star in there. And they can learn a lot more from this image than they can from this. So that's why scientists push to get good imaging resolution as well as good spectroscopy. Okay, the biggest challenge for us on Chandra was the mirrors. Now, recognize that due to the analysis that we performed early on, yes, this was all theoretically possible, but we had to be able to polish the surfaces of those mirrors, those grazing incidence mirrors, to an accuracy of on the order of angstroms. And okay, that's pretty small. Can we measure that? The answer is no. At the time, we couldn't even measure how accurately we needed to polish the mirrors. So that tells you that, boy, we've got our work cut out. We had to work with the National Institute for Standards to figure out how to first measure how accurately we can polish it, and then ended up polishing the mirrors. And polishing as a process, getting down to that smoothness, clearly is a huge challenge and takes a long time. And so that was probably our biggest challenge, is to polish the mirrors. Metrology is the science of working mirror technology and getting the surface figure of the mirrors correct. So we had really the key to success is developing 3 different types of metrology measurements that are independent, that allow you to cross-check, because you can get into, because you're talking about things that you've never built before and you're pushing the state of the art and you don't know how to measure it. The key there for an engineer should say, okay, I need not just one way of checking my work, but I need at least 2 ways and preferably 3 independent ways of making sure that I'm doing the right thing. So when you're pushing the state of the art, a good lesson is try and get into a position where you've got more than one independent check of your analysis to make sure it's correct. So that was a very big challenge for us. And again, that's kind of how it goes down. This is the general shape of the mirrors. And here are the mirror pairs being assembled. And of course, one thing about the mirrors is when you're talking about that surface finish, you can't just assemble it in your garage with dust around. So you have to be extremely clean. And believe it or not, one of the dirtiest things in a laboratory is a human. And so a human has to be almost completely covered to prevent any kind of accumulation on the mirrors themselves. So in fact, we had to limit the exposure time of humans to the unpolished and polished mirrors during this time frame, because contamination is an incredible problem when you're talking about the the atomic scales of polishing the mirrors. And again, mentioned that the important thing is to make sure you're doing cross-checks in the metrology as you're going along. Because again, you don't know exactly what you're doing. I mean, on paper, yes, you've got an analytical solution that tells you the right answer, but you've never done it before. You've never built it before, and you don't know how to measure it. So you've got to work on building confidence that, okay, your analysis is correct. How do I know that analysis is correct? And so you've got to think about a sanity check, if you will, to make sure that those are correct. And of course, the best way for proving that it's correct is test them. And that's what we did. We, mandated by Congress, we tested the mirrors. Now, the thing about that is, okay, so I test the mirrors. I'm testing the mirrors in a 1G environment. So even after the test, how do I know that those results are correct? Because the 1G deflection, even though you think it's small, it does affect the mirror performance on the ground versus in orbit. And another thing is the finite source distance. You can't get a source that's infinitely far away on the ground just because of the nature of putting a source out there. So our source was about, I think, a quarter mile away. And we had to make analytical corrections to compensate for how we expected the spot size to change because of that finite source distance. We had to analytically correct the image on the ground to compensate for the 1G effects of the mirrors. And so even a test, you'd think, okay, go test it. Well, it's not straightforward, because even in that test, that's not a true representation of how it would work on orbit. So it's not, it's a lot more complicated than one would think.
What'd you use as your X-ray source?
Various things. We had some monochromatic X-rays at various wavelengths. We had registration X-rays, iron. Certain wavelength of iron is a big one to use.
You don't have a picture of the big tunnel?
I think I do in here. I've got a picture of it and I can talk about it. But that's another thing, is when you're testing, okay, how well do I know my source? And that's all factored into verifying that you've got the performance correct. Because if your source is, all over the place and you haven't characterized your source well enough, then how in the world can you say that the mirrors are that good? So we did end-to-end testing, and again, you don't just look at the raw data and say, yep, I'm there. You have to, even in the ground test, a lot of times you have to massage the data and compensate analytically for factors that you can't control. And the key to success there is good systems engineering. And a lot of that is because of multiple separate parties, academia, nonprofits, and foreign groups all involved in the workings of ACSAF. You've got to make sure that you've got a team that works together. Lesson learned, as I mentioned, perform multiple cross-checks, either via test or analysis with a different tool as possible. Another lesson learned is let more than one group perform the review. A lot of times for Chandra, we had the Marshall engineers, but we also contracted SAO down the street to kind of independently assess using their own software tools where we were. And that was a good idea because sometimes we had good ideas that we could incorporate and sometimes they had good ideas. But it gave us a sanity check when we both matched and we both felt good. There's also no substitute for direct test or measurement. Analytically, we have wonderful tools nowadays, but they will never take the place of testing. Another thing that was very important for us because of the iteration cycle with headquarters on funding is make sure that you keep the science or the scientists that are part of the mission informed and part of the decision-making process. One would think, and one would like to think that, okay, this is a technical project, all things are technical. No, there are personalities involved, and there are human responses involved, and so to keep the team together, you need to make sure that the science is informed and supporting your decision-making process. A lot of times that's overlooked, but it is nonetheless very important as you're building a project. And the final lesson learned is, as we're going through and making those mirrors, you construct what's called an error budget. And you say, okay, I'm going to allow, you assume perfect performance, and then you kind of step back and say, okay, I'm going to allow imperfect performance in this region, and I'm going to allocate that imperfect performance to thermal design. I'm going to allocate imperfect performance to the inaccurate knowledge of knowing the source positions in the sky. I'm going to allocate some error budget to flexing of the optical bench. I'm going to allocate some error sources to the difference between how long the focal length is and how long I think it is. And so you take each of the error terms, and for Chandra we probably had 100 or more, and you go through and you verify that your assumption in that error budget term was correct. And usually for the critical ones you did it in more than one way, more than one method, so that you were sure that you had those error terms defined. And the end result was we had mirrors that performed better than expected. And as a result, the payoff is just wonderful. This is a time-lapsed series of images, and supposedly this wavefront was moving out from the source pulsar at significant fractions of the speed of light, on the order of 20 to 30% of the speed of light. So that was pretty cool. If you need more information, just talk to Jeff. But that was a pretty big payoff. The next challenge that we had was the programmatic challenge. And again, as I had mentioned, the normal process of going through a program and a project is you're first trying to size the mission, and really you're sizing it for cost. And that's very hard to do when you're building something new, and that was a very big challenge. And so we changed a lot of things, but eventually the key or the critical thing that you're trying to do is, okay, I compromise on this, but I want to still try and maintain performance. We maintained our imaging resolution performance and our registration performance. And we compromised on a few other things, but we maintained that performance. And note...
This is probably a good time to finish this slide. And
yeah.
We'll take a quick break.
Okay. Note down here that we also needed to reduce the weight by a factor of 2. from our original designs. Our original designs were pretty simple aluminum structures. Our final designs were the best composites that we knew how to make at lowest weight, and so that optical bench, that tube, was all composite. And so that's the kind of weight reduction scheme we had to go through. Now, also, all of the fittings, that means all of the brackets that we use, were also composite. And another challenge that we had is analyzing the stresses in a complicated composite fitting. Very hard to do. Didn't have techniques to do it when we started. We had to, as part of the process of building this telescope, we had to go through and learn that and develop those techniques. Okay?
And just before the break, I just want to point out, I hope you're all catching the incredible parallels between, this project, a complex technological process, and the sorts of things that we've heard about the systems engineering of the shuttle. Where right from the weight problems and composites, new materials, new ways of analysis, right into the intervention of Congress into the engineering process. I mean, it's all there, and I think whenever you get involved in a big space project, you can expect that those things are going to happen, and they're probably going to happen in the exploration program as well. Okay, 2-minute break, and then we'll start up again. Start up again?
Okay, let's see. Okay, we were talking about, for us, the next biggest challenge was programmatic, and that is not atypical. You have to work that early on, and typically, especially the more expensive missions, do go through this as a typical part of the life cycle of a project. Yeah.
You say systems engineering was cut, even the budget was cut, or was it eliminated completely?
The budget for systems engineering was cut, which translates directly to the number of folks at the contractor site working systems engineering was cut. So we were challenged, and what we did at Marshall was we offset with NASA civil servants doing functions and tasks that the contractor would normally do to compensate for that. So that's what that meant. Typically, systems engineering, very important thing. If you talk to folks in the trade, almost everyone has a different idea of what all is encompassed in systems engineering. But the point is, there probably are a number of things that almost everybody would agree are part of systems engineering, and they're very key to executing the program and the project. They're really the glue that holds all the subsystems together. And I'll probably talk more about it, but for good systems engineers, you have to be able to communicate well with all the other subsystems and all the other stakeholders, including the science when you have a science mission, including the users when you have a manned mission, including safety and everybody, to make sure they're all connected, and be able to challenge, smart enough to be able to challenge the subsystems when they really have their own ideas on where this needs to go, and it's not really in concert with everybody else. Okay, weight reduction did have some impacts, as I mentioned, using lightweight composites, and that was a challenge in and of itself. We also dropped 2 of the SIs. Another challenge was the science instrument module, which was all composite, and it had the capability of adjusting focus and translating. So it had 2 degrees of freedom, but it needed to be reproducible in terms of motion on the micron scale over the whole orbit environment. So that was quite a challenge in and of itself to be able to do that. I mean, just kind of a flavor for the things that you have to deal with is not everybody had the same analysis tools. So universities like MIT and like SAO, had different structural analysis tools for their hardware than the contractors did. So, okay, now when you do a coupled loads analysis, which is you pull together all of your stress, all of your structural analysis models together in one place, and you go through a loads assessment all through the whole element. Well, to do that, you need a model from you, I need a model from you, I need a model from you, but you're in California, you're a company, you're a university, you're another company, and you have to make sure they all play together. And a lot of times there is parochialness with company A, I'm not going to use anything but my model. And university says, well, I can't do anything but what we've been doing. And University C says, well, this is the only thing that'll work and you guys are crazy. That's not that bad, but that's the kind of thing that you have to deal with as a systems engineer. You have to make sure everybody plays together. And sometimes you have to go through and work the best solution that may not be the optimum solution for each piece, but it is the optimum solution for the overall answer. Again, getting the programmatic challenge behind us, a key thing is also setting allocations. I talked about the error budgets. Another good thing that the systems engineer does is it allocates various important resources. And one that every spacecraft does is weight. Weight, power, and data are usually some of the three of the important resources that are allocated. For scientific telescope missions, another one is error budgets for scientific performance. But the key to that is good weight allocation and good iteration with each of the elements that you've allocated the weight to keep up with them, to make sure, yeah, they can meet that, or looks like they're going to exceed, so I've got to go borrow some of that allocation from somebody else. And I've got to take away from Peter, if you will, to pay Paul. So systems engineering, in going through that, making the initial allocations and keeping up with that is a critical factor to making sure you get to the final answer. And if you do that well, then usually you have less of a problem getting to the final solution. To compensate for the loss of systems engineering, we established technical oversight panels, which were NASA employees at our center. We controlled at the project level the internal ICDs. Now, what's an ICD? It's an interface control drawing, because when you have company A developing an element and University A, where they come together is an interface, and you have to document that interface, not just mechanically but thermally. What's the heat flow across the interface, the data across the interface, the power, the signal characteristics across the interface, the data flow, what data is going across the interface. So, and as you can realize, that as both of those things change, you have to change the interface. So you have to keep up with that. And a lot of times, good systems engineers will recognize the further away in location it is, the harder it is to interface with the two parties. So when you're in California, it's one thing when they're in the same town. It's another thing where they're in the same country, and it's another thing where they're across the water when you're integrating an international partner. So as systems engineers, the factor is the closer you are, the better it is, because I can just go in a car, go across the town to talk to and to go get out the drawings and talk about the drawings, versus in California, that's a plane ride. But in Europe, the time difference allows you to only be able to talk to them for a few hours a day, because that's when your work shifts overlap. So it's a lot more complicated interacting with folks in Europe interacting with folks in Japan, in India, because of the time difference and because it's very far away when you have to sit down. So those are kind of the challenges as systems engineers that you should think about. So lessons learned: set your resource allocations early and continue to monitor them and work with each of the owners of the elements of those allocations to make sure that they're meeting their allocation. As you recognize, it's a zero-sum game. So when somebody goes over their allocation, somebody has got to be reduced. And, you know, if it's very difficult sometimes to negotiate that reduction because engineers typically want to hold their margin. They don't want to release it. They want it because they're not yet confident in their final solution. But to make everything play, sometimes you have to take away from them and reduce their margin to be able to let somebody else survive, if you will. So it's not an easy thing, but attention to that detail is important. Maintaining strong systems engineering group is important for that reason. So if I have a lot of pretty dominant subsystem managers, let's say, you know, I'm building a power system and I need this much weight and I need this much thermal capability. Okay, that's good, and they may be very good, but what they're doing is, if you have a lot of dominant subsystems and no central systems engineering as traffic cop, there's no check and balance. And so that dominant thing may work very well at the expense of the integrated performance of everybody else. So that's why systems engineering is so important, to balance that dominance and to balance weakness where you have weakness. And for Chandra, hard work pays off when you get it right. Technology, a lot of times NASA will build a spacecraft, a science spacecraft, and the spacecraft itself usually isn't pushing the state of the art. For Chandra, it was a little different. We pushed the mirrors, and there are a few other things we pushed. But typically, it is the case where NASA pushes the state of the art on the instruments. Better sensors, better CCDs, better processing electronics. And Chandra was no different. Usually, it's a embellishment from something that's flown before on a different spacecraft, only now it's better. You know, we're getting it bigger, we're getting it more resolution. It's takes less power. There's usually a stepping stone. And for ASIS, the one that was built at MIT, ASIS used charge coupled devices in an array size that they've never been built before. And so that was a challenge. Also a challenge was, in order for the CCDs to operate, they needed to be cooled to minus 100 degrees Celsius, 120. And in addition, they developed a new way of clocking out the data from the rest of the CCDs that have been built, so that had better spectroscopy performance and a very low noise signal chain. So they're always going and they're always looking at, well, on spacecraft X, this CCD was flown, and it may have been a 512 by 512. Well, you know, it's pretty easy. I can stretch it a little bit and work the substrate in 24 by 24. Well, usually it's the case where it's not as simple as you think, and there's always problems. So in particular, technology should be a warning flag to systems engineers to say, okay, typically it's not as simple as you think. So make sure you're paying attention to these new developments or these stretching of new applications of existing technology. Because, for instance, one of the things that you get bit by is, and we got bit by, is radiation susceptibility. Thermal extremes for multi-layer circuit cards that have to operate at minus 120 C on one end and room temperature on another end. low yields for those new types of CCDs. Yeah, I can just stretch it, make it 1024 by 1024, but where I was using 90% of the batch, now I'm only using 10%. Just because I can't get one that big to work out and to be smooth and homogeneous. ESD sensitivity, because they're getting bigger and bigger and thinner, it's much more susceptible to electrostatic discharge. And simple things like, okay, my yield in the wintertime, because the humidity in the air is lower, I have less of a yield in winter than I do in summer. And so that's what we found out. And there's also mitigating effects that you can come and put humidifiers in and compensate for that. But those are the types of things that you have to worry about that can come and bite you with new technology because you're doing something new. We also had, because of going down to 120 to optimize the performance and to get the very low noise, we said, well, we need a radiator or a sunshade, and lo and behold, flying on the shuttle in certain attitudes that you have to verify, because in some off-nominal events, you can instead of being deployed on day 1 of a mission, you get deployed on day 3, but you have to go across the terminator, the sun terminator, frequently, and you get a little glint of direct sunlight on these sunshades, and therefore you have to analyze what the temperature extreme and what the effect is going to be. And lo and behold, we see that we had delamination on that case. But here's a case where it's an off-nominal event in the shuttle that we have to design for and we have to compensate for, even though chances are we'll never see that design case. But it's a lot of times the programmer or project manager has to say, well, I'm gonna suck it up and I'm gonna make the change for that small eventuality, or I'm gonna risk it based on cost, and we're gonna try and preclude that eventuality from happening. So a lot of times it's not cut and dry, it's a guessing game, it's a balance, it's based on judgment, past performance, and a lot of other factors to say, boy, that's so low probability of occurrence that I'm not going to worry about it. And that number, that threshold is never defined. You have to define it as a project manager. So just kind of a picture of what the instruments look like. They're the CCDs. This is the long stretched away, and that's for the spectroscopy measurements. That's where the lower energies, actually the higher energies in the middle and the lower energies go along this wing and along this wing, that you get the energy spread. And there is the imaging devices that are used when you just want a good image. On HRC, there's the detector right there in this diamond-shaped thing, and it's operating off of a completely new and older technology than the CCDs. The instrument of choice has been this for probably 70-75% of the observations, just because of the capability that this allows you not just an image, but the CCDs also give you some rudimentary information on energy. And so that's why this is preferable over this one. On HRC, we talked about ACES. We had a low noise signal chain. On HRC, we never had 3 microchannel plates tied together and linked together, and we had that challenge. We also had very accurate event timing, so I could, when we have a pulsar, I know exactly in registered time when those pulses are occurring. We had spacecraft charging protection for new technology problems and spurious noise susceptibility. Spacecraft charging, to keep the mirrors nice and warm at plus or minus half a degree C across the entire mirror surface all around it. Required thermal blankets on the outside. Well, the thermal blankets were susceptible to charging up and discharging with popping. And so the question is, okay, is that going to affect my instrument performance by incorrectly registering a photon event every time these blankets discharged? So we had to go through a test campaign to verify that no, this discharging of those blankets electrostatically would not affect the imaging performance at the detector level. So, I mean, that's something that we didn't even think about before. But lo and behold, we came up with it. Yes, these things are going to discharge, they're going to pop, so is it going to affect our measurements? Those are the kinds of things that you run into. Again, good systems engineering and sound communications are the key to getting through those. Ensuring participation, keeping parties informed, encouraging teamwork to be part of the team and to help contribute to its success. Lesson learned is establish standing interface working groups with mandatory participation from the SIs. The SIs kind of have a different paradigm. The science instruments are usually built by universities. And the universities are typically staffed by grad students and some full-time engineers, but usually the paradigm and the thinking process is a university atmosphere. When you have companies, it's a completely different interface, very regimented, very by the book. We've done it before. This is how you do it. And so different cultures, you have to make sure they blend together to produce the final product. And a lot of times that's not technical, that's human interaction and making sure they all work together. When problems occur, recognize that you need to go outside of the project office to get help. And this is typically done at NASA. If we're working, if Marshall's managing a project and we've got a problem with CCDs, the key to success is recognize, well, Ames Research Center in California has an expert in CCDs. Call him up on the phone or bring him down and let's talk to him to get his expertise in on this project. NASA does good on that. It does go to where the expertise is, not just at another NASA center, but it may call experts across the industry or across academia to come help with a problem. The foam problem on the shuttle is a pretty big problem, and we've called experts from around the country and around the world to try and help understand what was going on with the foam. So that's something that NASA does well, is it brings in experts and it doesn't think that it knows everything locally. And that's something to keep in mind. If you don't know an answer, don't just try and think of it yourself. Go get the answers from somebody who might have experienced that before. And encourage teamwork. A lot of times programs suffer from the culture clash between different paradigms and different cultures. And that's especially the case between academia and industry. It's also evident between international partners and industry. And of course the payoff is, this is a spectrogram, the counts per bin, number of photons per energy level, and as you can tell, very sharp and very well defined peaks for where those lines are. Okay, next challenge was integrated testing. Integration is always a challenge. How in the world are we going to integrate this whole thing? The logistics of who does what when, we must choreograph it. Okay, here we've got instrument A coming in, we've got instrument B, we've got the gratings coming in, we've got the iSim built at Ball Brothers, we've got California building the optical bench. okay, where are we all going to put this all together and test it out? So that's always a challenge because, again, you've got different players involved in different pieces, and you've got to make sure it all plays together. And the key there is to create a working group to make sure you address every aspect of integration. You plan very much ahead of time. You choreograph everybody coming in to make sure you've got everything covered. And in integration, always, always, always takes longer than you think. You always plan assuming, well, nothing's going to go wrong, so this test takes this long, and this test takes this long, and this test takes this long, when in fact, as is always the case, you always have problems in testing. Anytime you're matching two boxes together, especially electronically, a lot of times you have problems. So testing is always something that you should make sure you have enough time to do troubleshooting and plan for failures and not plan a success-oriented schedule. Even the best laid plans, TRW planned the integrated testing in a vacuum chamber, and during observatory integration, TRW couldn't hold the schedule because guess what? First thing that goes when you're in a money crunch is testing at the end. And you say, why do that? Because they say, well, we had 6 months of margin in the schedule, and you've eroded that margin. But that margin, you haven't really defined anything to go into that margin. So, okay, well, hypothetically speaking, if everything goes okay, I don't need that. Well, okay, so you take it off the table, and it gets eaten away. And that's what happened. It got eaten away. They couldn't hold schedule. It caused, in this case, by antiquated EGSC and software, but it's typical of a paradigm that says, okay, I create schedule, you got to try and preserve the schedule and fight tooth and nail to keep that reserve in every step of the way. Because in integration and test is where usually you get behind. When we got behind, the recovery is daily focus on schedule. Every day we were on the phone going over what was to occur that day. 24-hour operations 1 year before launch, continuing all the way around the clock. We changed the INT integration and test lead out at TRW. We brought Marshall NASA engineers in to help TRW do it. And we had a technical presence help out at the test site. So we've got a contractor, we hire a contractor, and the contractor's supposed to do the job, and lo and behold, the contractor's not doing the job. So we could take a step back and say, whack them on the head, you're not doing the job. Or you can go in and say, we got to get this job done. We're going to go and we're going to send folks over there that are technical folks that will help your guys work these problems and work the issues and work the integration and get this thing done. And so that's what we did. That's kind of a typical schedule. We have an EMC comprehensive acceptance test. That's just a functional test going through all of the paces. EMI is your kind of electrical susceptibility to noise. When you have a Palm Pilot or a cell phone and it's near a computer or near some device, you hear this chattering. That's what that test is all about, to look at interference patterns and look at whether you're susceptible to noise. We have an end-to-end test. That's where we get a compatibility van and we make sure that we can communicate with the Deep Space Network dishes in Goldstone and Madrid and Canberra. We have, that's our pointing and control systems polarity test. Did we mount the gyro correctly? Or is it upside down? Did we mount the reaction wheel correctly? Do I have the spin vector pointed this way or pointed that way? You think that's pretty simple, but in fact, on the box, it doesn't say arrow pointing up. You have to actually test it out. And NASA has screwed it up before. We do an acoustic test and then a pyroshock test. Acoustic is you blast it with acoustic noise. and the noise couples and creates vibrations. Especially you're worried about thin films and large surface areas that are exposed to the noise pattern, the wavefront. So we painted the whole spacecraft with a huge woofer. I mean, it was enormous, just to see the vibration and what would happen to make sure that it was okay. And we have the solar array full motion test and the low gain antenna release test. We've got mechanisms. Mechanisms are typically things that fail a lot or don't operate the way you thought. So we want to test those hopefully in the environment that they would see in orbit. That means if it's cold, if it's exposed to a plasma, we want to try and duplicate that on the ground. So typically that's what we do with mechanisms, yeah.
I was wondering if you had like a separate like satellite that was for testing, and then you kind of knew that all the other parts were the same, where you tested the actual components, and then how far do you push it?
Good question. Typically what we do is, if in the old days when we had a lot of money, we would build what's called a qualification article, which is basically a test article for the whole thing, and the qualification article would match 1-for-1 the flight unit, and we'd test the heck out of that qualification article. Nowadays, with money problems, typically we don't do that. For selected components where we're worried about the design, we'll develop a qualification article at the element level. But typically, we don't do it with whole spacecraft, not anymore. So, although the one exception to that is the structural test article. Usually spacecraft do build a structural test article that does look like the final flight design from the overall structure, and you get your mode shapes and your frequencies when you ring it and see how it performs, and you fold that back into your analysis. But that's probably the only case where you build a full test article for structural purposes. It'd be nice if we could do that. The DoD does that when they have a production of 1,000 units, but NASA nowadays can't afford to build a whole complete ground test article. Be nice, but sometimes we just can't do it. We'll do it on a selected element level. No, hardly ever testing to failure. We do test.
We talked about that with a shuttle, because J.R. Thompson was pointing out, like with the main engines, testing to failure was really critical for success. But remember, that's a very different operating situation than a satellite, where, you know, normally if the satellite can survive launch and the vibration is tested, the
Yes.
structural, you know, if that survives, then the operating environment is a lot more benign.
Now what we do though is we compensate for not testing to failure by testing to our expected flight environment plus margin. So analytically, or based on previous data, we determine what the environment's going to be, and we'll add margin to that, and we'll test to those margins. Most times we do pretty well. Sometimes we don't, but that's probably few and far between. And we've learned after 40 years of how to apply margin to our best analysis or our best tools that define what the environment's going to be. So that's kind of that shows you starting in October 87, ending in April 98. That was the plan. We actually took about 9 months more than what you see there because of all the problems that we had. A key point is when you press for time, don't cut corners. We did review all the testing, and we didn't delete any testing that we considered was mandatory. And in fact, we added systems testing to verify that we had total system performance, that we knew what this thing was going to do. We also added some testing, end-to-end testing in thermal vac, and added much more testing, end-to-end testing with the control center that will eventually operate. A lot of times you have, in the integration and test time, you have a different set of engineers testing this than will actually operate it in flight. Probably not a good idea. what you really want is to get your operators in flight operating and testing early enough that they can go through all of the gyrations of the testing environment and all of the idiosyncrasies of the hardware before flight, so that they're trained on the hardware and they know how the hardware performs. And so if you can, you want to try and get the operators to do the testing prior to launch. And a lot of times that isn't the case, unfortunately. Lesson learned, try to keep one integrated database along that theme of the control center for testing and operations, because what you don't want to do is to have a database for testing that then you discard and you create a separate database for operations. It's much better to have one database so that you know what the parameters are, and once you've verified them in test, they're the same parameters that you're using in flight. Also to define an explicit test and integration lead, review the approach, encourage end-to-end testing participations of the operations group early and often, and if you can, get the operations group at the control center to run the tests. And give adequate time for box level testing and data system integrated testing. A lot of times what will happen is you're running late on schedule, and at the box level I've got a multiplexer, and I had scheduled at the box level probably 300 hours worth of testing. Well, you know what, I'm running late. They're wanting me at the spacecraft level. Well, let me zip it up now. It's only had 50 hours, but now I'm going to the spacecraft. Lo and behold, now what you've just done is you've moved the problem further on downstream when it's much more expensive and it costs you a lot more money. So when I have a problem in integrated testing, guess what? The whole spacecraft stops until I fix this box. So if you can, try and do it so that you've got enough margin that you can test at the small box level before, in parallel with all of the other boxes, before you get to integrated testing. Okay, management. There were plenty of challenges in the management, and there's a term used is unknown unknowns. We didn't know at the time that money was going to be a problem with program restructuring. You don't know that you're going to have an integration delay. There's a lot of things that you really don't know. But nonetheless, you have to expect for and you have to plan for. That's why at the beginning of a project you create what's called reserve resources. In terms of cost, you usually have, depending on the nature of the complexity, the technology push, you may have 20 to 30% of cost held in reserve. Not applied anywhere because you don't know where the problems are going to occur. And you try as a project manager to hold on to that by tooth and nail and not release it if you can at all, and only grudgingly allow reserves to be used. Approach to success in that kind of environment is experience, getting top management that has background and experience, working closely with the science community, again focusing on teamwork. You'll see that as a recurring theme. Hold enough reserves so that when you're scoping out and you've got a lot of unknowns, that you have enough money and time to do them. Set it as high priority for the company or the organization that you're working for, and set the schedule early, and balance the need for maintaining schedule with the need to slow down and understand what your problems are rather than racing to the finish line. Okay, again, these are some of the good lessons learned. In fact, I just covered that one. This is what it ended up being, the ACSAF schedule, starting in around calendar year 92 with our SRR. There's our PDR, and there's our CDR, and the launch is even off the chart. But that's typically the kind of things that we go through, including in parallel your control center development back down here. as a mirror. I'm going to go, and actually I'm going to...
all of this would be posted, so I mean, these are really valuable lessons. So, in fact, any of you who eventually go into systems engineering and project management, take some of these lessons learned with you, print them out, and review them periodically.
And remember them. They're lessons of hard knocks. What I'm doing now is I'm now the project manager for a project or a mission called RLEP-2, which is Robotic Lunar Exploration Program. And that mission will be the first mission that NASA has in a long time to land on the moon. We're going to land a lander, and we're going to have some type of mobility device that will either drive into a crater or hop into a crater or crawl into a crater or walk into a crater and look for lunar ice that we think might be there at the South Pole. Now this is a great example of how things are done. We are given a couple of requirements to say, okay, we want to verify our precision landing capability in an unmanned sense, and we're going to use that technique and those algorithms for the future human lander. And we're also going to need you to go look at the ice, characterize it, and see whether or not ice is there. Now, why is ice so important? Ice is important because of the oxygen that you can get from the ice. And the oxygen's not so much to breathe, but it is for fuel or for oxidizer for propulsion systems. Instead of getting it at the Earth's gravity well, you get it at the gravity well of the moon. So that's our challenge. Now, when they asked that, NASA didn't exactly know what it would cost or what the cost profile would be. It might be, they originally designed it for a $400 million mission. They said, well, why don't you look at a $750 million solution? They don't know how many objectives we can meet. They also don't know, okay, this RLEP program is supposed to be robotic lunar exploration. It's really a precursor to the human missions. So they're not even sure how to use this program to help bring humans there. And so this is typical, as NASA doesn't exactly know what it wants to do, but it kind of puts out feelers to say, okay, try this. So it says, go start with this, go touch the lunar surface, characterize precision landing, and go see if there's ice there. Well, okay, go see if there is ice there. I can do that with one hop into the crater, one sample, and hopefully if the ice is there I can find it. Or on the other extreme, I can go with a rover, spend a year in the crater, take 1,000 measurements, and characterize the ice. Okay, obviously one costs a lot more than the other. So how in the world do you answer that question? Which one should you do, and whether it should be a mix? Those are the very things facing the project that I'm working on now. Not only that, one of the things is, okay, we're trying to get prepared for a human mission, and we want to reduce the overall cost and reduce the risk. We'd like to bring risk forward from the lunar mission, manned lunar mission, into the RLEP program and retire it in the robotic program. What that means is if I've got a technology challenge for a cryogenic engine, that means a liquid oxygen, liquid hydrogen engine for the lunar descent, I want to use that same engine, if I can, on this mission to work out the kinks. But how much is that worth to NASA? If that costs an extra $100 million for RLEP, is it worth it? There's no set answer. And so what we're doing right now is what's called a pre-phase A. Much like I showed you on Chandra, where you had that initial design and the final design, we proposed to headquarters with one design. That it happened to have a rover, it was nuclear powered, we went into the crater, and we stayed there for quite a while, and we very, very definitely characterized what was there. But it was expensive. Is that the right answer? We don't know. We're right now going through a pre-phase A that we're looking at other options. We're looking at kind of 3 classes of sizes, different solutions to get into the crater, different solutions on the size of the lander, its extensibility to the human mission. Like, for instance, right now we use Russian Progress vehicles to resupply space station. We are designing, or hope to design, a lander, a robotic lander that would do the same thing during human missions. It's not man-rated. It won't fly men, but it can fly supplies to the moon with one design. But that costs money because now I'm not optimizing design for a point solution mission. Okay? So during this time frame, there's a lot of unknown questions, and the answers aren't straightforward. So what we're doing is we're giving a series of options and rationale and capabilities for those options to headquarters. And we'll make a recommendation as to what we think is the best answer for NASA to go forward with this design, and here are the reasons. But it could very well be that they choose something different because there is no definitive solution to this problem, or this challenge, if you will. So it is very challenging. It's going to look probably a lot different now than it will when we actually launch it in 2010 or 2011. But it is something that we face now, and it's typical of things at NASA. It's more defined by how much money you can use versus what the requirements are. Sometimes the requirements do set pretty much the basic tenets of the mission, but other times it's driven by cost. And so right now we're in the middle of working that interesting and challenging problem for headquarters to develop what we think that mission should look like. And as you can envision, you don't really have requirements. You have a few requirements. You have a desirability to reduce the overall cost and reduce the overall risk of a human mission. But that desirability comes with a cost. The more extensible you get to the human mission, yes, you can make a big lander that gives you 2,000 kilograms of payload, but it's going to cost you more. I can make 1,000 kilograms of payload or 500 kilograms of payload and get the definition of what's in the ice, but then later on I'll have to design a new lander for getting other things accomplished that I want to get to on the moon. And is that the right answer? So you can tell that there's a lot of challenges with that. Any questions?
We talked about the cost, performance, schedule triangle. Now, do you have a sense inside NASA of how much they're pushing schedule at this point? Where's your flexibility?
They have, in their solicitation to the centers, they allowed schedule flexibility. They allowed cost flexibility. So here's a program that other programs, I will say, are generally more bounded than this one. This one is a matter of NASA not knowing exactly what the reason and what the purpose of the program is for. You know, you've got this general idea of going back to the moon, using robots first to prepare for humans, but exactly what does that mean? And exactly how do you prepare for humans? And how much is it going to cost? And when is it going to launch? And how many missions are you going to have? Are all undefined. Now, what we would do is we've already gone to the program that will fund the human missions to say, okay, what do you guys plan to do? What do you want to do when you get there? So we can take their mission design and say, okay, how can we help? We can help here. We can help here. We can pull this technology forward and fly it. The problem there is that they haven't thought that far ahead. They don't know exactly what they're going to do. And a lot of that is, okay, is there ice there or not? If there is ice there, we'll want to process it. We'll want to extract oxygen from it. So, as part of our solution, we do know that we have to answer that question. We also do know that we do have to demonstrate precision landing. But above that, they've given us a target date of 2010 to 2011, but they said schedule's not fixed. They've given us a cost generally between $400 and $750 million. And oh, by the way, if you can leverage other areas of the budget to help your mission do that, in particular technology, there's a separate technology budget. So if I can get technology to pay for a new technology development at no cost to the program, then I'll do that. And again, if we come in and say we have $1 billion mission, but it buys you $3 billion when the crew is ready to come, we think that's worth the investment. And then headquarters has to scratch their head and figure out whether it's really worth minimizing the long-term cost versus the yearly constraint that they're given by Congress and the pressures of Shuttle and the pressures of Station on the overall cost of the program to NASA. So it's real challenging. It's a lot of fun. We're going to have a blast. Or the next one's going back to the moon. And you'll probably be hearing more about it in the next couple of years.
Okay, thank you, Tony. So this was really the last of the lectures on systems engineering per se. Thursday is the last external lecture. Gordon Fullerton will be talking about test flying the shuttle. And hopefully by then I'll have the schedule for the presentations next Tuesday. Okay?